Swayam Prabha. Digital India. Educated India.
So here is now a tool, really nice tool. Actually, it's publicly available, and I've given Professor Aragapan the link. That's you can download, all of you, if you want, on your own computers. Yeah. So here is a nice program, and you can use it. We'll use it for this particular example, the one we just did. It's called Nonlin. How many of you work in seismic areas? Any earthquake designs anybody works on? Not. So if you work on earthquake areas also, this is a excellent tool because you see there is, of course, these are all earthquake acceleration time histories for American earthquakes, but you can easily import your own Indian earthquakes, especially Maharashtra, all those places where Assam, I think, Maharashtra in particular, some places you design, then you have to use, you can use it. But we'll just start with a new problem, and we've set up that problem in US, but you can also do metric units. So inches, and maybe we can go kips is fine. So you have here free vibration, right? We've looked at that. This is forcing function. We have seen that. Forcing functions are now, in this case, they are more for, we were using that for blast, but then it got also updated for blast load. So that's what we will use. If you're using earthquake, then you do ground accelerations and then incremental dynamic analysis for more specialized. And here you have a stiffness, several parameters. You have the weight, damping, then the stiffness 1, stiffness 2, strength. And the stiffness kg is also here. If you see the line going down, that is if you have softening. If you want to incorporate a certain breakdown into 1, 2 and 3, then you can incorporate softening to a certain extent. Other than that, you can use these 3. And if you do the blast load, let's go with the structure, the example that we just did. What was the weight of the floor? You can give me some number. So you click on this icon, and this was in kips. So what was the weight? So 8.5. After this nonlin, you might wonder why we went through all the lectures so far, because it's just a really nice tool. But you have to know what's behind this. So that's your weight. And then the damping, although it is 0, you can try, but I give a very low value, 0.1, that's 1%. Then the stiffness, what was the stiffness in this case? This is in kips per inch. How much was it? 81.8. So 81.3. So make sure the units inches and kips, so 81.3 kips per inch. And then, so it will automatically give you, your time period was 110 milliseconds we calculated. So this gives you 103 milliseconds. Then you have the frequency, the natural frequency in radians per second. And then I think that could be because of the damping, 0.1. Let's maybe change this to even lower. That might be where the difference is. No, that's not affecting. And then in the blast load, it's quite simple to apply, but you have to be careful on a few things. So this has a simple pulse. You can do bilinear pulses. So like if you're doing a wall load analysis, then you can do a bilinear pulse. So this is a simple pulse. Did I give you the pulse duration? Let's say the pulse duration was, first case, 20 milliseconds, right? Is that right? 20 milliseconds. And then the maximum, again the pressure pounds square inch. What was the PSI? 20, right? Or, okay. So that was 20 PSI. Now the tributary area, so we took 6 feet by 20 feet. So this is in square inches. 6 by 20 is 120. 120 by 144 is? No, 120 multiplied by 144. 17280. So then the lead time, so the lead time, that's your rise time. Really don't have to give, I just given one number. And the scale factor, the scale factor, if you're, that's for tributary area. I think if you're inputting, I forget, is it for PSI to MS KSI, or let's check that. I don't know how I forgot that, but the scale factor is important. Ramp time. Ramp time is your lead time is arrival time. Ramp time is your rise time, and the scale factor. This is we're already providing in square inches, so I think we leave it as 1. And then if you plot it, so this is your plot, and the duration. If this is 20 milliseconds is what the total duration, but this duration is basically how long you want it to run. Even if you run it for 100, we'll check on this scale factor. So if you see the ramp time is 0.1. So we'll use this, and then if it is purely elastic analysis, now we had a triangular load, again elastic analysis. If you, then you have to just do linear, then those things get blocked out. If you choose non-linear, you have to provide a strength. We'll see the next couple of days. By Tuesday, you'll be, at least for by Monday or early Tuesday, we'll see how to do some strength calculations. And then the stiffness, there is no real estimate. It depends on how, if the steel structure, concrete, or whatever you think is an appropriate stiffness you can provide. But if we run this, so yeah, this displacement is way high. I think, I know that's where, let's go back here. Clearly at so this is in, oh, okay, this is in milliseconds, pulse duration is in milliseconds. Damping force, you have the displacement. How did I forget that? It's been a long time since I've used it, but still. Oh, so it needs internet access for that. Let me look into that a little bit. I don't want to waste class time. The scale factor is what? I used to use 144, I believe. So that's why I put 1. Or this was converting, maybe it is milliseconds to seconds. Let me try that. Because all these calculations are in seconds, maybe it is that one. Let me try that. Okay, so seems to be more reasonable. So here what you see is you get a displacement of 2.526. We got how much? 2 point something, 2.77. Yeah, so that's the scale factor is converting from milliseconds to seconds there. And that's why specifically they've written these numbers. They've written it in milliseconds because I mean, that's a nicer number, right? It's 1 instead of saying 0.001 seconds. So that's the purpose there. And then the other things that you can look here is time history plots. So this is a linear displacement you have at a different, so here you can see the maximum response. You have to change the decimals for it, but you can find the maximum response wherever it is, and when you can find, you can do frequency plots. Here you can play around with it and see what this gives. You can then plot it to take it to Excel also. It's got some nice functionalities. You get this. So there are, we didn't have a damper, but if you want a damping force, we talked about that. You can get the damping because we gave 0.001 or something, right? So you can get that. Other things you can get yield. We haven't done any yield in this case, but and then if you now go back and we do another case where, what was the second one? The pulse duration was 60, right? So plot it and use and then run 5.49. What did we? 5.49? 5.3. So very nice tool to use. And we'll see when we do the yield part of it how to use this as a for basic calculations. Any questions? And we've looked at, for example, the effect of rise time. So remember this 5.3. So ramp time, let's say we have 5 milliseconds. Okay, before I do that, you can compare. So this is the displacement, and so the displacement is oscillatory up to, this is in seconds, times in seconds. We went up to 100, we don't have to go beyond. Now, so these are some other analysis if you're interested. It works in seismic. So now if I change the ramp time to, let's say 5, and then run it, let's see what happens. 5 point, it didn't change much, but the peak, remember, it doesn't change. But now the oscillatory part may be a little different. If you plot those two, you could maybe see the differences. Here we are not able to, but you can plot them and see the differences. What did we say? The ramp time is equal to TD, right? What was, it almost becomes static. What was the ramp time? Was very high, right? Tn in this case is 110 milliseconds. 110 times 3 is 0.3 milliseconds. So 300. So, well, let's give even 60 itself. Td equal to Tn. Duration is 60 milliseconds. Let's give that. And if I plot it, it's got inertial force plots, damping force plots. Yeah, you see how it has changed from 3 oscillations. The oscillatory response has reduced, but it has changed. And the graph that I had, it also shows in a similar way. I couldn't show it, but I'll upload a picture of the graph that I was planning to present. So we can do this yesterday's problem. We can work this in Nonland this afternoon and continue working on other aspects that we'll talk about. Just to explore, if you want, you have, that's your time histories. Other things it can do are hysteresis plots. There's no dissipation in this case. There's a little bit of dissipation, and then energy plots if you want. We are going to do some energy methods right now, and gives you a report that you can use, and something is wrong, so it kicked it out. Okay, so now we come to a topic that is used, is very interesting to you might see its usage not for design purposes, but mostly for assessment purposes. So let me start with why, where and why it is used. It is used to assess potential damage. Damage to a structure. And due to an applied pressure impulse or pressure time, instead of pressure time, here we take the pressure impulse load. You need to have standardized PI diagrams. It's commonly mentioned in this field. I don't know if in India they have developed these for Indian structures and materials. I mean, that's something I think if you want, you can consider this as a project for the future, Excel based, VB based, to develop, where you give a lot of sections and then it automatically draws. It takes a while to do it, but it can draw automatic PI diagrams. So this is just like it is based on a specific structure and its properties. When we talk of properties, we are talking of material and structural, geometry, boundary conditions, all those kinds of things. And it is based on the energy principles, energy methods. What we are going to do is just to spend some time understanding the fundamentals of what a PI diagram is. We are not going to be drawing a PI diagram. It is very difficult to draw a PI diagram unless you run hundreds of simulations. We'll see why. Energy methods and also impulse. So the really energy methods in engineering, as you know, whether it is civil or mechanical, is a extremely widely used principle for finite elements, is based on energy methods. So impulse, momentum principles. So if we, let me take a step back, quickly review broadly. You have loading a blast loading on a structure, and then you have the response. So the response of the structure is based on three different, you can either have a QS or a quasi-static. You can have a dynamic. We've briefly discussed this is a response regime. So the dynamic regime, quasi-static regime, or you can have an impulsive region response. Broad characteristics, TD is less than Tn here, and in this case TD is much greater than Tn. These are the two extremes. Again, we've seen wind, static are all. In terms of the equations, dynamic region is, the response is from solving the ODEs. It's really hard to predict. It's like, even in weather, they say you can predict the next few hours quite accurately. You can predict after 3 days fairly accurately, but it's very difficult to predict that 1 to 3 day range. Similar phenomenon even here. The dynamic, because there also weather prediction is solutions of differential equations or partial differential equations and so on and so forth. So same overall concept. Now quasi-static methods, you can use the work done equal to the potential potential energy principle. So that is the energy methods part of it. Whereas the impulsive response, this is where we use the impulse momentum principles. So let's look at both of them. It's a very different way of looking at it, very interesting way of looking at the same things we have done so far. And I have a couple of analytical expressions that I worked out yesterday, today to illustrate some of these points. So let's consider a scenario, the loading. Loading is, as we have seen, long duration. P naught and maybe X max. So the loading, even though it's not developing, it's not a static load, it's a quasi-static load. So in static load, you would go P naught. When you say pure static, it would be more, this is static. Here we are saying this is quasi-static. That's not a purely official definition, but in these cases, notice the difference. What's the big difference here? The work done, right? The work done is twice in that case. So load is not, it's not so long that it is developing. So we are not considering this scenario. Whereas here, the loading is P versus T. And let's consider now here the impulse, this is pressure versus time, but the impulse is, let's say I, is 1/2 P naught T. So, coming back here, the work done, we are considering a spring system. Here you have P as a function of time, and then this is going to go to X max or delta max. So, starting with the work done is equal to the potential energy. The work done is P delta max. I mean, you'll be off by a factor of 2 if you had taken it the other way, 1/2. This is equal to, what's the potential energy? 1/2 K, right? So, that's your potential energy. So, you get from here P is equal to 1/2 K delta max, or delta max is equal to divided by P over K is, we did all the differential equations, and here you see the beauty of energy principles. That's, if you've done courses in energy principles, this is the beauty of it. No differentially, and you'll see that very nicely in, but again, limitations, a lot of the limit, you should be able to get the energies, internal energy accurately. I'm not saying this is for everything else, it works for everything, but you see that now delta dynamic or delta max by delta static is equal to 2. Here now we go with impulse is momentum. What's my impulse? 1/2 P naught TD. And what's the momentum? Of course, you have a mass here. M, momentum is mv naught, right? So, if you can leave it in two forms. So, from here I get V naught equal to, so this is one starting point. V naught is equal to I by M, or in this particular case P naught TD divided by 2M. So, remember both scenarios, we will use both of these cases, both forms. For V naught is, what is V naught? Initial velocity, the velocity with which. So, then we also have to use, once we use the impulse momentum, then we go back to the kinetic. So, the transfer mechanism of an impulse is velocity gets transmitted as, instead of work done, it gets transmitted as kinetic energy. So, we start with, I have already written the word. Kinetic energy is stored as potential energy. So, that's how you build. So, the kinetic energy is 1/2 m V naught square. Potential energy is still the same, K multiplied by delta max. Again, all elastic systems. You can have PI diagrams, principles for elastoplastic systems as well, but this is. So, continuing to now, I can write 1/2 m, and I can either, let me see what I want to leave it as. I'll use the second form. V naught is P naught TD by 2m square is 1/2 K delta max square. So cancelling these and taking the square root, so I get square root of m P naught TD by 2m is equal to square root of K delta max. Then keep in mind P naught TD by 2m is square root of K by m, which is omega n. So and omega n is also 2 pi by Tn. So I have these two expressions. Combining them, I can get delta max divided by, there are two more steps. Let's skip those steps. P naught divided by K is equal to pi TD by, see, this also gives you that the behavior in the impulsive region is a function of TD by Tn. And in fact, it does give you a number. The shock spectrum, right, we did. So this gives you something similar to the shock spectrum, again for a triangular loading. So what we have now, let's compare both of them. Static, here you get delta max is by delta static is 2, and correspondingly what we have is delta max by delta static is pi TD by Tn. Let's just look at a couple of cases. Help me with this, please. So TD by Tn for, let's say, 0.2, let's go 1.0, and let's say 1.5. So what is the ratio? If you can just calculate, multiply by pi, .63. This is 3.14, right? And so this doesn't quite correspond to the shock spectrum that you saw, elastic shock spectrum, but it gives you some range of applicabilities, at least for 0.2. See, what region are we analyzing? Impulsive. Let's go back here. 0.2, what was the number we got there? 0.2 is 0.63, right? So what does it tell you? For, of course, tells us principle not applicable here. These are not we would go only in the lower range, but clearly valid here. First of all, TD by Tn of 1 is not even in the impulsive region, but this simple principle works very well for, here is a simple equation if you are looking for to predict deflection in the lower regions, you already have it. So, okay, So if I plot, let's do this plot and then do another analysis. So if I plot this, I plot delta dynamic divided by delta static and Td by Tn. For the region here, for low regions, this is pi Td by Tn, and then here it is, so this is the impulsive region. This equation is linear, pi Td by Tn, and then quasi-static it is asymptotic at 2. So the word, what word did I use just now? Slipped it in? Asymptotic. So the quasi-static region, this is the quasi-static asymptote. And here you have the impulse region asymptote, impulse asymptote. What happens in the dynamic region? We talked about, this is the dynamic region, QS, this is I, this is use ODE solutions, non-len things. Non-len is nothing but an ODE solver for you, applied to different cases. People have spent time on developing their own softwares in MATLAB and posting it. I know of a colleague who's done that. After some time you stop maintaining it. All this is very exciting to develop. Ultimately usage is limited to a certain group of people who work on this area. So you don't get as many likes. Maybe we should hire, I saw an advertisement in today's paper for content creation as a company by itself. They say we can get you so many million likes. I was front page ad, full page. So maybe we should also contact them. So I found this is a very nice example. Okay, how do you apply this to, what are some standard structures we use? Most structures can be broken down into simply supported cantilever, right? Anything else is an approximation. So, it's a build-up, but in many cases you can get a really good approximation using this. I'll show you for one scenario. You can try for simply supported later on. So, we'll call this energy solutions for specific structural components. I think this could be part of some of the tutorials are also developing as content is. Some of these contents I have not included in any of the courses, this course in the past. So this is all new, and I think we can base a tutorial out of this material now. So one is an elastic analysis. These are it also depends on the type of loading. I'm not and boundary conditions, of course. But we'll see how to use this principle for a simple case. So in this example, let's consider a cantilever. And the cantilever has L, B, and T. And this is subjected to either, like we did in the previous problem, that's why I said depends on the type of loading. We'll keep it generic. So let's say it is subjected to loading here, then you know it is PL cubed by 4 EI. So consider impulse loading to start with. We'll do the quasi-static part. I'll also give the elastoplastic analysis. So the impulse I is mv naught is 1/2 p naught t. So from here we get v naught is equal to I by m. So this was the first. What is the second one? We said kinetic energy equal to potential energy. So 1/2 m v naught square is equal to 1/2 k delta max square, or 1/2 m v naught is I by m square is 1/2 k times delta max square, or simplifying a little bit more, I square divided by 2m, and this could be the reflected impulse. Say this is, let's say you calculate or you determine the reflected impulse. So IR divided by 2m is 1/2 k, again delta max square, so what I get from here is the delta max is equal to I r square, right? No, we took, yeah, IR square by m, km square, no, delta max squared. So the square goes away. That's what I was wondering. So if I take that out, I get square root of km. So now the mass is rho multiplied by the volume. The moment of inertia is, I forgot. Okay, BD cubed by, making sure you're awake, BD cubed by 12. So I can write this as the, now K, this is where I said it depends on the loading, right? It could be PL cubed by 3 EI if it is a point load, or some equivalent load multiplied by L cubed by EI. I don't remember the constant, some C1, let's say, right, or C0, some constant. So in all these cases, here you have a constant. I can write my K is equal to some constant L cubed by EI. So dependent on the loading, I can you can generate those constants for whatever you want. So now I come back here and let me expand Km before I take a square root of it.
Is it expression for delta or k?
I've just taken L cube by 3 EI, this part of it. Oh, yeah, you're right. Yeah, EI by L cube, right? You're right. My bad. So this is some, let's just put it as some constant EI by L cubed. C naught is dependent on the loading. Thank you. So expand Km. So Km is a constant C naught EI by L cubed, and the mass is rho multiplied by B d L. So let's continue to expand this out. This becomes L square. So C naught, then you have E multiplied by rho, and now I is BD cubed by 12. So now if I club the geometries, B square D power 4 divided by L square. Am I missing anything? 12. So let's make this constant C1. So keep it generic. So I like to separate, you see what I'm doing here? I like to separate components, geometry, properties of material properties. You put them all in one clubs, different clubs, it becomes easier to work with it and visualize. So now what I get is, this is Km. So square root of Km is C2 square root of E times rho multiplied by B d square divided by L. So what do I get now? Combine this one, combine this one, and I now get a nice expression without going through differential equations. So I get delta max is C2 L over D IR by square root of E rho multiplied by D. So the L by D ratio for a cantilever, remember that's important to define, longer than is a cantilever, so bring that down. Rho is the density of the material. So now you have impulse driven deflection equation. Everything else is geometry and boundary conditions. And once you start combining numbers, all these 3 and 12 and all these things are there, 48, ultimately you might see the range of C2 becomes very small. You won't see much variations in it. You can try a couple of different cases and see. And here, so C2 is this much. And I didn't have time to get to a numerical part. Maybe we can take this and put this, we can develop an equation tutorial on this, right? It might be able to do that. Might be a good exercise. Do you agree? Then let's look at the other scenario, quasi-static. Again, applying impulse momentum and energy principles. So we are looking at work done equal to potential energy. So the work done in this case, quasi-static, it depends on again how long TD is. Work done could be either 1/2 k delta max. So the work done is 1/2 k delta max. And on the other side, you have potential energy is 1/2 k delta max square. No, work done we said was k delta max. Potential energy is 1/2. So not k delta max. I knew something was bothering me. I knew this equation didn't look right. This is P. Okay, now we are clear. P delta max. So what we get from here is P equal to 1/2. Of course, we know this principle, K delta max. So P over K. Now if you see K 1/2, the K is the same as before. We can use K is equal to C naught EI by L cubed. And delta max, and so this is 1/2 C naught E by L cubed. This is BD cubed divided by 12. So you can lump all of these into a constant C1, then multiplied by E, and then you have B d cubed by L cubed. So let's say B d cubed by L cubed. Am I missing anything? Delta max, right? So this is P is so from here I get delta max is equal to the applied, now this is in terms of the applied pressure. Previously we considered, you have to be consistent with units. This is just a derivation, so more in terms of the principle and not exact equation, because the numbers C1 all come into play. So this is C1 multiplied by the P naught. So let's say a constant C1 multiplied, or C2, let's say 1 over C1 multiplied by P multiplied by L cubed by D cubed, or L by D cubed, multiplied or divided by 1 by EB. So this is pressure driven deflection equation. All these, why are we going through this? I mean, you could do non-lin for everything and be done. You know, you need numbers, you need some kind of ideas, answers to fall back on, and that work. So that's one of the reasons. And understand the fundamentals, of course. So you can similarly you can do elastic plastic behavior. We know that we are not having elastic behavior for everything. What would be the difference for elastic plastic behavior? How would your P delta, let's assume rigid plastic. Have you heard of rigid plastic behavior? Yes, no? Yeah. So, it's going to, elastic behavior we all know. Rigid plastic, it's good to know because these are some things that we can apply in non-net. So, this is rigid plastic. So, basically up to P naught, this is what we would call delta Y is the yield deflection. And delta Y can be calculated as P naught divided by K. So, in your problems as we apply it next week, you can calculate your yield deflection based on the resistance of the of whatever structure it is divided by the stiffness of the structure. And then this is delta max. Remember that your ductility ratio was delta max divided by although it's kind of a misnomer. Again, ductility, again you could be dropping the whole way down, and the ductility ratio is still the same, right? Which is why in concrete, now in steel this is maintained. Concrete masonry, it drops down, which is the reason they don't use ductility ratio. Another reason to not use ductility ratio. So, use ductility ratio wisely. So, when you now once I have drawn this, this is rigid plastic behavior, elastic of course and rigid. Most commonly all your steel, I section steel behaviors is rigid plastic behavior. So, what is the difference between elastic and elastoplastic? If you are doing, let us say, the quasi-static principles, where would the differences be? So, which calculation does it affect? The work done, right? See here the work done is P delta max. Now the work done is one half P delta Y plus P times delta max minus delta Y, where we know delta Y is equal to P divided by K. So, it adds another layer to it. Now, you can all, this is your yield stress. So, this is Py. The internal, I guess not the work, the internal energy in this is not this is the, what have we called it, work done potential energy. Because the work done is still P delta max. P naught, work done is P naught delta max. So, note the distinction. So, work done, this is Py, work done is P naught delta max. So you can go to town on this in this analysis. Once you will get x max. So if you, I'll give you the final answer in this case. You get delta max is equal to, if you do this is and similar, let me, before I do this, it's so perform a similar analysis for impulse region, and you can get for the impulsive region the delta max is the applied impulse square L square divided by 4 Fy rho dq. So even for that region you can get, if I see if I can get some numbers done. In the first case, let me mention, forgot to mention, C2 here is approximately 3 in that range, just to give a range of ideas. Now, so once you have, we haven't touched the impulse momentum diagrams. So in practice, again, this could be a little different from the earlier definitions. The response regimes can be broadly classified based on what we have done now. Let's say this is your region. Qualitative time limits and quantitative time limits. So if it is impulsive region, what we have seen is the delta max by delta static is pi Td by Tn. Here this Td by Tn very small, and we had said Td by Tn is 0.1 in terms of omega n Td 0.4. Then the dynamic region, it is from 0.4 40, and the quasi-static region, here delta dynamic by delta static is 2. So omega n Td is greater than 40. So we had seen in terms of Td by Tn as 0.1, 0.1 to 1 and more than 1. I think I'm just trying to see if I'm missing anything from what I wanted to say, but yeah, okay, all that is covered. So let's get introduced to the concept of pressure impulse diagram, what it is. trying to see, we might not be able to go all the way, but that's okay. 12:45, right? Yeah, it's about 15 minutes, okay. So, there are other applications, I don't know, I'm trying to think of, I know I've encountered maybe thermodynamics or trying to think of what else, but maybe you can help me when you see this. So very specific to, when I say specific, in loading applications. We're not talking of thermal or electrical or those kinds of, I'm sure there are, maybe seismic there are. It's not a spectrum for sure. So this is, keep in mind, it is not a spectrum. Sometimes you have to say what it is not. You identify something by saying it is not this, it is not this, it is not this, it's not this, and then you can define something better, right? So definitely this is not a spectrum. And it is not, again, not applied in wind or seismic applications. And so now we're beginning to look at blast in, again giving a context to it. You've seen these, but blast is either a pressure, the two variables are pressure and time, or pressure and impulse. This is a history plot, whereas this is two specific variables. Peak pressure. So there is a difference in when you would apply pressure time history, and there is a difference of when you would consider pressure and impulse variables. Now, maybe I should say how to prepare this later. Okay. The purpose of, we call this a PI diagram. Is one, to generalize it, it's a diagram, it's a plot, a single plot with multiple graphs in it, multiple curves in it. So, single plot with multiple curves for a given structure. So, we generalize it to all, that's the important part, loading on the structure. So, you generate a PI plot for columns for specific configurations, it's specific to that, but once you generate, it's something like a moment interaction curves in some ways. You can think of PM diagrams in columns, yeah, in some ways. So, it's generalized to all loading, and there's slight differences. PM diagrams are not necessarily used to assess damage, but the purpose here is to assess damage, there it is to actually design. So, there is an application difference, but similar in idea. Then the generalization is done by non-dimensionalizing and the variables. Basically, the pressure and impulse. And finally, this plot, the PI plot, is used to assess or predict damage given pressure, impulse, loading. Not to design a structure. So, where is it useful? You have an existing structure and then you know its reinforcements, whatever details. Once you know that, then you can generate PI diagrams. Once you have that PI diagram generated, then you can assess for different scenarios of blast loading, what would be the LOPs, what would be the damage to that structure, all those. So, it is post assessment of structures. This is an extremely useful tool. How to non-dimensionalize impulse and pressure. So, the next step in this is to non-dimensionalize impulse and the response. So, on the x-axis, if I were to take impulse, the impulse has units of pounds, seconds, right? Or you can have Newton second. I need pound second, Newton second here. In terms of quantities that we know, and if you play around, you would have done non-dimensional analysis in fluid mechanics or some other courses. So, play around with your variables that you have and you get this terms that we have seen quite often, x max square root of km. It also non-dimensionalizes it. It non-dimensionalizes Newton seconds. And then on the y-axis, if look at, and we'll change this x max, this is x static. Which is nothing x max k divided by p naught. So, you can look at this as x max is 2 x static, which is 2 p naught divided by k. So, you can say x max 2 p naught divided by 2 p naught divided by k x max, sorry, k x max equal to 1. No, 1 is not there. So, we can say 2 p naught by k x max equal to 1, and here you can say x max by I impulse by x max km, this is also equal to 1. So, now if I plot these two, the asymptotes you will see come through. So, remember these, when we plot x and y, what do we think of? Anytime you plot 99 99.9% of the time when you plot y as a function, y and x, what comes to mind? Y is a function of x, right? But keep in mind here it is not. Y is not a function. It will help you. For me, it took a little while to wrap my head around what this represents, because then I realized I'm thinking y is a function of x. But here y is not a function of x. There are two independent variables, x and y are two in being plotted in the same graph. So say this is 1.0, you're plotting I divided by 2, x max square root of km, and here I plot 2 p naught by k x max, and I have this 1 and 1. So between this it forms so this is a PI diagram, a PI curve. It's called an iso damage. What does iso mean? What does the term iso damage mean to you? So here damage is deflection. So if you were to describe this curve, one sentence, we'll take 2 attempts. What does it describe? An iso damage curve represents what conditions? It is the, yeah, go ahead, you're right. Locus of the damage points. Wait, you almost got it. First time you had it right. It is the, okay, I like, let's develop that. Let's put a definition to it. It is the locus of the points representing, what did you say? Yeah, representing the same damage or deflection caused by various combinations of pressure and impulse. Very nice. Don't think you'll find this definition in any books, but well expressed. So time really flies. So this could be, for example, let's say delta max equal to 2 inches. This could be a curve for some other delta max. Let's see. So what does this mean? Various combinations. If you look at it, you are saying P naught TD P naught 1 TD1 represent same damage. So it's not a fixed P naught, it's not a fixed TD either, but the P and I can keep changing. But this, so if you plot a 3-dimensional, so what are the different regions? We'll maybe spend one more graph. So we've seen that it has two asymptotes, and will so here is an asymptote. So this is what is called as the quasi-static asymptote. So this here represents the pressure in some ways. Here it is the impulse. So the quasi-static or the pressure asymptote. Say this is 1.0 non-dimensionalized, and this is the impulse asymptote. Various regions are, let's say this is region A. Region A represents no damage at all. Region B is here. Region B represents the region where, as you increase the pressure, right? So it represents impulse regions. Although you're increasing the pressure, is it damaging? No. Regions where increasing pressure does not we are talking damage is the limit. There is a limit to it, right? We are not talking, yes, deflections are different, but it's not now, we are assessing damage. So I can increase the pressure and there is no, same thing in this region, C. This is low pressure region. C is increasing impulse or the duration does not damage the structure. Low pressure region. And region D, here is where, so D is the region where there is, again this is the QS, quasi-static. D is finally where damage beyond the limit, the limit of the PI curve. So one thing it does not do is to help you calculate delta max. That's another thing that this is not going to, you're not going to use a PI curve for delta max, is to connect these two. So next class is connect PI diagrams to LOPs. We used to have a tool that would generate these diagrams, but unfortunately that works only on Windows 7. And yesterday I was talking to Professor Aragappan, and he was saying there's a way to simulate Windows 7 on a Windows 10 machine, but I don't have the program now. But anyway, that's out of distribution also, so I'm not allowed to use that also. But it also gives you ideas of how you can generate. We'll talk a little bit more about it on Monday.